Hello and welcome to 5 Minutes of Postgres. My name is Lucas and today we're going to talk about creating functional dependency statistics to improve planned cost estimates in Postgres. Now this is a very practical episode today looking at a problem that I myself encountered last week where I was trying to optimize the estimates we're getting for a particular query inside our own system. Before we jump into the example, I want to show you just quickly what we want to talk about here when we say extended statistics. In Postgres, you have two types of statistics that the planner makes use of when it tries to understand how many rows will be matched by a particular query. The first kind are single column statistics, and these are always automatically collected. You don't have to do anything for that. That happens automatically in the background as part of a process called auto-analyze, and auto-analyze will automatically get data from your tables to assess how frequent certain columns are. For example, it will calculate things like the n distinct number here, which then represents of the total number of rows, in this case, how many unique entries are there. Now, we also have extended statistics. And the big difference with extended statistics is that the Postgres will not do this automatically for you, but it oftentimes makes sense to create these statistics in order to improve planner cost estimates or influence query plans into the right direction. The statistics type we're going to talk about today are functional dependency statistics. These help the planner estimate when you have two columns that are dependent on each other, which means for a given value in column A, you will always, or most of the time, have a particular value in column B. It helps you tell the planner about this relationship between two columns that the planner otherwise wouldn't know about. We create these statistics is using create statistics command, and we specify the dependencies type to collect these functional dependency statistics. And then we look at two or more columns that are part of that statistics object, where the planner will then collect the statistics. We then need to run analyze, and then we can actually see the statistics collected. In this example, we can see the column position 1, which is the zip code, has a clear functional dependency on the column 5, which means that for a given zip code, you'll only ever get one city. Now, I want to show you an actual example where I ran into this in our own database because I find it paints the picture pretty clearly where you might see this yourself. On our database here, we have a table called issues, and this tracks issues that pganalyze finds in our customers' databases where it then flags common Postgres problems. On this table here, you can see that we associate the data to a particular organization, to a particular server, and in some cases to individual databases. One of the queries is where we look at a particular organization ID. This here is our own internal organization ID. And then if we just look at the explain here, you'll see in this very simple case, we have an index on this, and it estimates that there's 250 rows returned. Now, another case that we often find ourselves doing is we actually query for both of these columns, right? We specify the server, but we also know the organization ID, and so it's included in the query. Now, what Postgres does by default is a bit of a problem here. So you can see in this particular situation, which is actually rare, it uses a bitmap and, so it gets one index scan on one index, and then the next scan on the other next. And so you can see it estimates that on the one index, we'll get 250 results. On the other one, it will get 110 results. Then after the bitmap end, just one result, which is not true. If we run and explain analyze here, what you'll actually find that clearly the result of this query shows that there's 488 rows. The misestimate here is pretty big. Really what's happening here, what Postgres does behind the scenes when it calculates selectivities, if it doesn't have extended statistics, it will just multiply out the selectivities of the individual parts of the query. So you can imagine that internally, it's a very small number between 0 and 1. In this case, it's probably like 0.0003 or something. Then it multiplies that with the other number, which is also very small, like 0.0004. And then what happens is because those two numbers are multiplied, they actually become smaller, which is how we end up with this row estimate of 1. Now let's run create statistics on this table on the two columns that are referenced. So we'll run this, and then we'll actually have to run analyze because this just registers the statistics object in the database, but it doesn't yet execute the actual collection of data. What we'll find is that surprisingly enough, it hasn't changed. Now, the reason for this is on this particular table, I know that the default statistics target is not going to be sufficient. And so what I'm actually going to do is I'm going to increase the size of that statistics object. So I'm intentionally going to select more statistics, which is going to take a longer time. Now I run analyze again. This is going to be slower than before, but what it does behind the scenes is it gathers a lot more data. And so this will help improve the functional dependency information so we can clearly show to the planner that these two columns are correlated. Now that the analyze has finished, I can rerun my explain. Now we have 500 rows estimated, and remember from before that that's close to the actual row count return. Now to end, I want to show you briefly how this actually looks like behind the scenes in Postgres itself. When Postgres executes a query, really the part to look at, if you're ever interested in the nitty-gritty details, is the clausesel.c file. That's really what drives these selectivity estimates that then defines how many rows you're getting in your query. The general approach how this works internally is that first Postgres will try to apply extended statistics to as many clauses as possible, then only to those parts where it didn't apply them. It will then use a regular method, which is take the product, aka multiplication, of the individual selectivities. And this is where you'll get the misestimates, because that oftentimes could be wrong. Postgres will then look at the actual extended statistics information. In addition to the functional dependency statistics we looked at today, this will also supply what's called multivariate MCV lists in more modern Postgres versions. These help you improve estimates even further for the most common values in your table. In the case of the functional dependency statistics, though, we ultimately land in this function here. It will first try to find the strongest dependency between the columns involved. In the situation where we're talking about city and zip code, for example, it will prefer zip code pointing to the city versus the other way around. In the situation with organization ID pointing to server, it would prefer server pointing to the organization ID, because that's the stronger correlation. And with that, we'll essentially say, first, multiply the strength of that functional dependency with the selectivity estimate for the leading column, essentially. In the case of zip code, that would be 1 multiplied by zip code. Then it would say plus 1 minus f, that strength of that dependency, and then multiply it with the regular selectivity. And so what that means is the stronger the dependency, the more it biases all the way towards the leading column being the value it uses. Versus if you have a very weak functional dependency, it will act more like the regular code. In a sense, it's very simple, but this really makes a big difference in your planner cost estimates. And the reason it often matters to have an accurate row count is because this does influence how Postgres chooses which join order to use. For example, if you have a nested loop, this greatly influences which of the tables gets queried first, and then which of the tables is on the inner side of the nested loop, which then again influences index usage. If you see row misestimates, I would highly recommend looking functional dependency statistics, and also consider looking at the actual statistics data to get all the details. Thank you so much for listening. This was 5 Minutes of Postgres. I wish you a happy Thanksgiving, and talk to you next week.